I'm explaining about the eset syllabus. Overall, we have the eset total marks is 200, and that we have divided maths is 50 marks, physics is 25, and chemistry is 25. Total marks is 100, and engineering subjects also will be there, and 100 marks for this. And maths divided into many topics. Unit 1 may have the matrices and partial fractions, 5 2 marks, and Fourier series, trigonometry, complex numbers, analytical geometry, differentiation and applications. In differentiation applications we have more marks in 10 marks. Integration and its application is 7 marks. Differential equations 7, and total is 50 marks. And this for chemistry also we have 25 marks, and the topic name is structure and atomic structure, chemical bonding, solutions, acids and bases, electrochemistry. In this more we have that electrochemistry is the more marks, 4 marks. Water technology is 3 marks, corrosion 2 marks, polymers 3 marks, fuels 1, environmental chemistry 2. And same has given in the physics also. Just check it in Google and search it. Is a 2021 syllabus. And civil engineering subjects we have engineering mechanics, strength of materials, theory of structures, RCS means reinforced cement structure, surveying, hydraulics, irrigation. TE means transportation, irrigation, engineering. W means environmental engineering. 10th is steel structures. In the below link, this is the ESET syllabus. For every year the syllabus TS and AP will change. For AP extra we have Fourier series, they will come in exam, but in the TS we not get the Fourier series in maths. I am explaining about strength of materials today. Mainly I am telling about properties of materials. Strength, maybe properties of materials we have 10. Strength is nothing but ability of a material to resist a load, which is nothing but tension or a compression, shear, or any gradual load or any sudden load, and impacted load, or any different types of load without undergoing deformation, which is nothing but if a material is applied at load. 1 second, I will show it. If the material I taken, then apply the load, it is any compression or any tension, then the material should not be going deformation. That is nothing but a strength. Stiffness is nothing but load resistance capacity of a material unit deflection, which is nothing but stiffness is denoted by K, and the load is denoted by small w, and the deflection is denoted by y, small y, which is nothing but when the material is applied by the load capacity per deflection. Stiffness is a member of Young's modulus, which is nothing but capital E. Elasticity, ability to regain dimensions when applied load is removed, which is nothing but when the load is applied, the dimensions will regain immediately, which is not if I taken one material, if the iron load applied tensile loaded is applied, the material is again which is nothing but regain its original dimensions, and when load is applied also. Plasticity means ability to retain dimensions when load is removed, which is nothing but this opposite to the elasticity. Ductility is nothing but ability of a material to resist a tensile load undergoing the permanent deformation without failure. Material with large deformation at the failure is ductility, which is the main point, which is nothing but when the material is applied in the tension, which is nothing but tensile load is nothing but the material which is opposes the load to the material, which is nothing but opposite to the material when the load is applied, which is nothing but permanent deformation without any failure, having a large deformation at the failure is ductility. Example we can call as on gold, silver, platinum. Ratio of strain at flexure to that of yield for mild steel is 250, which is nothing but for a mild steel curve, which is nothing but stress and strain curve, we have the ductility of a strain of a flexure of yield, which is nothing but 250 value. Ductility is another definition is ultimate strain by yield strain. Ductile materials are deformed into wires, which is nothing but gold is we can draw in into the what's mm, thin wires, that is nothing but wires deformed into the wires. Malleability. Malleability is nothing but property of a material by which it can be beaten in and rolled into sheets and plates, which is nothing but the material we can do and sheets also or any plates also. Ability of material to resist a compressive load undergoing permanent deformation without failure. This is the malleable property, which is nothing but the material which is resisting a compressible load. Compressive load is nothing but which is the material which in the what we can say either sides, both either sides are which is in the same plane. The load is acting. This is nothing but opposite to the tensile load. That is nothing but compressive load. Next, all ductile materials are malleable, which is nothing but the materials which are in beaten into wires that can be drawn into a malleable also. But that malleable which is nothing but plates and sheets which cannot be malleable, which cannot be drawn into the ductile materials. This is the keynote point. Mm, Plastic response of materials to compressive form is malleability, which is nothing but malleability is the nature of doing the compressive load only, no, not having any, and also plastic responses for this. Factor of safety in working stress. A ductile is yield stress by working stress. Yield stress is nothing but I'll showing the one graph in the mild steel. This is a stress strain curve. This is the elastic property. This is the upper hill point. This is the lower hill point. This is the upper hill point. UP. When the which is nothing but when the factor of safety the ductile is nothing but yield stress by working stress. In the for the material of the factor of safety for the material or a brittle, which is nothing but ultimate stress by working stress. This is the yield stress. This is the ultimate stress up to the ultimate when the this is the breaking point up to the ultimate the load is applied when that in the brittle or a material in the factor of safety. Hardness is nothing but ability of a material to resist the scratches and indentation, which is nothing but if the material is taken, if the material you taken when the scratch it, which is nothing but scratch it on the material, that is nothing but a hardness. The material are difficult to machine, which is nothing but difficult to cutting in a machine, but can be utilized for cutting other materials. Examples we have here MCS. MCS is nothing but medium carbon steel. HSS examples high speed steel. HCS which is nothing but high carbon steel, and CBN which is nothing but cubic boron nitrate. This is the most hardest of the material is diamond and abrasive etc. Most hardest material is the diamond only. uh, Diamond is cutted by diamond one quotation is there, no? That's most hardness of the diamond. Toughness. Strength plus ductility. Strength is nothing but ability to resist and with not going in a deformation. Ductility is nothing but which can be drawn into voids, or we can say that when the load is applied in a tensile load without going the permanent deformation, at that fail at not failure. Statics test, which is nothing but toughness is area under stress strain curve up to ultimate point. This is the ultimate point. This is a stress. This is a stress which is denoted by sigma, and the small ev denoted as a strain. Sigma is denoted by stress, which up to the ultimate point. Stress strain curve. This is nothing but a static test. Dynamic test is nothing but toughness is energy under stress strain curve up to ultimate, which is nothing but static test we can consider as an area. This is the lines showing in the graph. This is an area where this is an area how much area is occupied in the stress strain when we test it in the graph or when we test in the UTM machine. UTM machine is nothing but universal testing machine. In that, how much area is occupied when the specimen is kept it or a mild steel is kept it. That is the meaning of the static test. In dynamic test, which is not how much energy is occupied in up to the ultimate point when the specimen is kept in a UTM machine. That is nothing but a dynamic test. Resisting impacting loads without failure. These are the properties for the toughness. Next, note point. Total energy absorbed by a body within elastic limit is called as an resilience. Total energy, which is nothing but elastic limit, is this is the elastic limit. In the red mark, I am showing the stress strain curve, and up to the mild steel is nothing but an resilience. Ability of which is not the total energy is absorbed of a body within elastic limit only. Within only elastic limit, the energy is totally absorbed. Ability of a material to absorb energy in a deform elastically and release energy upon loading is resilience. Another definition for this: maximum energy stored by a body at elastic limit is known as some proof resilience, which is nothing but maximum energy stored in a body, which is nothing but maximum stored in a body, which is nothing but at the elastic limit is known as a proof resilience. Modulus of resilience is equals to proof resilience by volume. Modulus of resistance we can written as an MOR, and proof resilience is equals to, it denoted by a U and volume is denoted by V. Brittleness, which is nothing but ability to fail under impact load. Impact load, we have three types of load: impact load, sudden load, gradual load. Sudden load is nothing but, if we take an example, when stone is fall on the ground, suddenly the stone is fall, which is nothing but suddenly. Gradual means nothing but impact load means by forcefully we applying the load on the bench or any taking the material. If I am taking about any stone, big stone, and forcefully I am applying the load on the bench or any table, impact is applied, just nothing but forcefully applying, that is nothing but impact load. In the brittleness, ability to fail under impact loads. Example, I say that glass, cast iron. Creep is the most important, which in many competition exams, gate, anything exams, eset, most examples is asking in creep is nothing but is depend upon four parameters, mainly four parameters. This must be mind it: constant stress, strain, time, temperature. These four parameters is depend upon the definition, and these four parameters must be important. Mind it. Statement is not but change in the material with time under constant loading is creep, which is nothing but in the definition when the time and under constant loading is appearing, we can observing, that is compulsory the definition of the creep only. Continuous deformation, another definition: continuous deformation with time under sustained loading is creep. This is the note points of this. The definition we can ask any different method also. This is the main also. This is another definition, which is nothing but main definition also. But by comparing two definitions, this is the most important definition. Slow and progressive deformation under constant stress at high temperature is called an creep. Fatigue, which is nothing but after number of cycle of reverse load failure of a material is fatigue failure, which is nothing but if the take and load in the number of times you are applying the load, number of cycles you are applying, which is nothing but rotations you are applying the load in the reverse of the failure, it is nothing but fatigue failure. We can say that a member which is subject to reversible, which is nothing but reverse action, reverse tension or a compressive stress in fail at stress low, that ultimate less of material. Next, assumptions we have here. First assumption, the material is continuous, there should be no voids and no cracks present in it. just I am taking a material which is nothing but any material. We can assume that I am taking an example, small example, a hood or any. You can take any column also, any examples of iron, etc. I'm taking the material is having, this material is continuous, not having any voids also, which is nothing but not having holes or not having any cracks in the material, which is nothing but for first assumption. And as for second assumption is the material is homogeneous and isotropic, which is nothing but homogeneous is nothing but material originates from single source. I'm taking small example, I'm showing in the figure, which is nothing but the materials originate single, which is nothing but only having the one point only. This is the one direction of the load which is applying in the load. Single load is originating the same line and same source also. It's just not about homogeneous. We can say that examples timber, iron, aluminum, etc. Isotropic, which is nothing but same directions, the directional property, same direction, which is nothing but I'm showing the figure. In this direction also is same, downward direction or any upward direction or any we can say cross or inclined direction. The material is same. Having the properties also same in any direction you considered also. That is nothing but iso. Yeah, isotropic. Iso in the word we can say that in Greek word iso is nothing but you can say that same. In the word only we mentioning the form definition also. Examples. We have the fine grade materials, iron, brass, glass, steel, etc. And we have the one note. All the homogeneous material may not be isotropic and vice versa, but few homogeneous materials, which is nothing but base metals, will be a isotropic, which is nothing but all the homogeneous materials, which is nothing but wood, timber, iron, aluminum, which not be maybe a isotropic, but few homogeneous materials, which is not the base metals we having it, will considered as an isotropic. Next, some other types materials, heterogeneous materials which have more than one base materials, which is nothing but alloys is made up of brass and copper. In that way we can call as now more than having the base materials, which is considered as an homogeneous have only one material, which is not but aluminum only having. Alloys we have more than metals which can brass and copper, which is made, we can made as an alloy also, which is nothing but steel. ఏమంటాం స్టీల్ బిందెలు అంటాం కదా అలా, దట్ మేడ్ అప్ ఆఫ్ ఓన్లీ alloys only. This is nothing but heterogeneous material. Orthotrophic, which is nothing but in mutual perpendicular direction materials are different. I'm showing again small figure. I'm taking that mutual perpendicular, this and this mutual perpendicular, which is nothing but 90 degrees. The material which is perpendicular to that each other, the properties are different. Which is nothing but example, we can say that all layered materials, timber, graphite, mica, etc. And another material anisotropic, or we can say the non-isotropic, or we can call as an allotropic, which is nothing but at that point in all direction the material properties are different. We can say that isotropic. In isotropic, in the opposite one, we can say that's anisotropic. An example in the one point indicating that in all directions or also the material is very what we can say different, having the different properties, which is nothing but examples. We can say that materials with having a voids and cracks, which is nothing but voids is nothing but holes. Next, assumption 3, the which is nothing but the principle of superposition is valid. Principle of superposition is nothing but the combined effect of several loads acting simultaneously on linear elastic structure is equal to the algebraic sum of effects of each load acting individually, which is nothing but if I am taking a one linear material or any, the number of loads are acting in this or which what will load sim what roll load, UDL load, point load, that so much loads are acting by considering only in single line, which is nothing but algebraic sum in a combined effect, and we can taken as in individually we taken, or we can taken as roller road we can consider. Here some superposition is valid, the linear elastic materials, and second one for very small deformations and slopes. For circular shafts, which is nothing but solid and hollow subject to torsion, and only for gradual loads is valid for the superposition. And superposition is not valid for longer or a slender columns. It's undergo laterally load buckling, which is nothing but uh, buckling, which is nothing but by taking that we having the two axes, x and y axis. The material is taken. For example, I'm taking the column. This is the column. By applying a load or any fixed beam or any fixed support, we can take it. This is a fixed support. The when the load is applied, the deformation occurs like this. When which is not but the we can say in this direction, we can say that which is nothing but breadth and depth we have. In breadth side we have the less, so that in that side lateral is small, which is the least dimensions. No, that's why the buckling will occur in this step one. Non-circular shaft subjected to torsion, not valid for the impact loads. This is that I'm showing the figure. This is an what we can say point load and rollers, and this is an uniform bearing load, and this is an momentum. This with all these supports or this all the loads are considering in a individually. It is not that combining in a one line only. That is the position. That is the principle of the superposition, and not valid for deep beams. It is nothing but deep beams torsion developed due to loading, which causes a distortion in shape, which is number D is greater than 750. This is the next example for the deep beam, which is nothing but we can take an as a circular. We have in the when we're twisting the in circular, we have twisting the material. We have which is not considering in the superposition. Sinking of supports, which is nothing but axis get distorted. Long columns, which is nothing but fixed. Right, before on I told this example, which is nothing fixed beam. We have ring buckling occurs, torsion of a circular shaft. This is the figure which shows that shape gets distorted, shape remains circular. When we're twisting in a circular, it's the same shape. When we're rotating any direction or the taking any circular rod or any circle ball, we twist it or you can rotate in any direction. The shape is remains same. In the shape of the rectangle, we can take the shape is get distorted. Assumption 4, self-weight of member is ignored initially. Assumption 5, Saint Wade's principle is valid. Saint Wade's principle is nothing but the father of theory of history. It states that sudden change in the cross section should be avoided, which may lead to stress concentration. It's nothing but sudden change when we take and when you apply the load taken in the cross section wise. In that sudden change in the load, which is nothing but stress concentration we get should be considered, should be prevented by fillets or chambers. Assumption 5, materials obeys Hooke's law, which is nothing but deformation, strains and stress are assumed to be within elastic region. This is the stress strain versus diagram in the mild steel consideration. This is elastic region, this is a plastic region, and this is the fracture region. In that elastic region, we consider as an Hooke's law. The assumption 5. Types of stresses, we have small important not points. Working stress of a mild steel specimen is calculated using factor of safety on yield point stress. Factor of safety at the ductile is yield stress by working stress. Factor of safety at the material or brittle ultimate stress working stress. These are all the important points. Cup cone deformation is usually indicating the ductile failure. and Oops is valued upper proportionality limit, which is nothing but stress is directly proportional to the strain. Law of proportionality of stress and strain in the material was formulated by Robert Hooke. For most material, stress relation and strain under elastic limit follows linear dependency. Material is material is loaded behind a point stress, which is nothing but it loses a tendency to retain its original shape. And a thin mild steel wire is loaded incrementally till it breaks. Extension load with increasing in a load will be increasing uniform first, then increasing also rapidly. Isotest, the specimen is supported at the cantilever beam, while its sharpest is supported in the simply supported beam. And there's nothing but in this question's main important points mainly asking in the competition exams. Notch face is isotest is facing the striker, while the charpy test the notch face is positioned away from the striker. Ratio of maximum load to the in the BTech we have the nozzle test, ISO test, the notch test. In the BTech we have. In the diploma we not having any test also. In the laboratory we done it ISO test and the CRP test also. Ratio of maximum load to original cross section area of a test piece is ultimate stress. This is the figure I'm showing. Strain hardening like cling. This is the rigid fluid and ideal fluid is nothing but stress strain. This is the mild still diagram. This is up to that. Firstly, it may changes into the what we can say elastic region. This is the yield strength. This is the ultimate strength. This now in this we can call as an up to here we can call as an strain hardening and neckling. At that point, cross mark we can call as an fracture. Hence modulus is nothing but rise and run, which is nothing but slope. Stress strain modulus of rigidity, modulus of resilience. We can say that in the before I explained modulus of resilience we can consider as an maximum what we can say maximum load is applied of considering at that elastic region only. We can say that modulus resilience. Young's modulus is called as a stress strain. Elastic constants we have Young's modulus or modulus of elasticity E is equal to linear stress by linear strain. Shear stress or shear modulus or modulus of rigidity we can denote it as an C or N or G, which is not much shear stress or shear strain. Bulking or bulk modulus or dilation constant, which is denoted by K, which can say that direct stress by volumetric strain. E is equals to which is not he is nothing but Young's modulus, which is nothing but stress by strain, which is nothing but stress is nothing but load by area, and by E is nothing but the change in dimension by original dimension. We can denote it as a delta L by L. E here having the some values for the elastic constant. This is having the highest elastic constant. Diamond is 200 gigapascal. For the steel having the 200, and copper we having just nothing but Cu 120 gigapascal. Bar brass we having the 100 we can call as a bronze 80, aluminum 70, timber or nothing but a rubber 10 gigapascal. Next, maximum elastic is in small questions here. Maximum elastic is in nothing but we can consider as a modulus of elasticity by comparing all my friends done mainly mistake with taken in the rubber, not in wrong answer. This diamond is the correct answer, which is nothing but by observing the before diamond having that elasticity more, which is nothing but 200 gigapascal. We consider mainly rubber having a 10. So rubber only have absorbing elasticity, which is nothing but సాగదీస్తున్నప్పుడు రబ్బర్ సాగదీయడం ఎక్కువ అవుతుంది కదా అనేసి in that mind they think it. So diamond is the correct answer. Note, for isotropic material, E is greater than K is greater than G, which is number modulus of elasticity or bulk modulus or what we can say modulus of rigidity. Axial rigidity just not but A increased increased and delta L decreased. E is nothing but stress by strain. This is sigma by E, and delta L by L is nothing but P by AE. Delta L is equals to PL by AE. Newton's units for this Newton. For axial rigidity we can denote as an EI. For axial rigidity we can denote it as an AE. If EI increases means Y is decreased. Y is nothing but deflection. Units for this Newton per mm square. I am taking small what we can say any cantilever load and applying the load at the point load at the free hand. When applying the load we get the deflection, which is not if E high is increasing. Flexure rigidity increase means the deflection is decreased. Torsional rigidity is nothing but GI. There is no units having the Newton mm square. Here also Newton mm square for the flexure rigidity, and the formula for this T by L is equals to G theta by L, or we can written as GJ by L is equals to T by theta. Poisson's ratio. Poisson's ratio is nothing but ratio of lateral strain to the lateral strain. This number with sign change. Uh, linear strain, which is nothing but longitudinal to that axis. This is the laterally. This is the linearly, which is nothing but lengthwise the load when the lengthwise is considering, which is nothing but linearly is considered. This is a laterally, which is not the breadth or depth we considered when the section is rectangular section. We knew Poisson ratio we denoted as a nu 1 by m, nothing but E strain by E lateral by E strain, which is not we having that Poisson ratio, we having the values by considering negative to the 0.5. You have the some values here. Nu is equals to negative for the genetic materials, which is nothing but humans we considered. Nu is equals to 0 for the croc. Croc is nothing but which is like a wood. And next nu is equals to positive for engineering materials. Nu is equals to 0.5 for elastic and compressive material, which is nothing but water. Examples rubber, wax, timber, water, etc. For isometric we have the 0.25. For the hard material and brittle material we having that less than or equal to 0.25. For the steel we having the 0.27 to the 0.3. And for the small soft material we have the greater than 0.25. For the small question here giving, for the cast iron we having that Poisson ratio is 0.27 is the answer, and that for aluminum we having the 0.33. For the concrete we having the 0.15, and we having the small elastic constant relations. He is equals to 2c 1 plus 1 by m, or we can written as 2c 1 plus nu. Nu also we can written as 1 by m only, which is not nu is nothing but Poisson's ratio. C is nothing but modulus of rigidity. E is nothing but modulus of elasticity. E is equals to 3k 1 minus 2 by m. E is equals to 9k c by 3k plus c. Nu is equals to 3k minus 2c by 6k plus 2c. These small questions, find it. Important points here we have independent number of elastic constants. For isotrophic we have 2, and orthotrophic we have 9, anisotrophic we have 21 elastic constants for independent. For dilute and incompressible materials we have question here. And thank you, and subscribe my channel and share it, and please like it.